Now we'll discuss mathematical induction before leading up to Cantor-Bernstein theorem. Induction is the key method to a type of proof called proof by induction, and it goes as follows. If T of n is a mathematical statement depending on the number n in the natural numbers, and if T of 1 is true, and if T of n prime is true whenever n is true, then T of n is true for all n in the natural numbers. Indeed, if E is the set of those n in n for which T of n is true, then by hypothesis 1 is in E and n prime is E whenever n is in E, so by the induction axiom E equals n. There will be many examples of this application in the future. Now to prepare for the Cantor-Bernstein theorem, let us consider comparing different cardinalities. The natural comparison of cardinalities of sets is defined by setting the cardinality of A less than or equal to the cardinality of B if there exists an injective mapping F from A to B. This is well defined, since if A prime is equivalent to A and B prime is equivalent to B, and you have it that the cardinality of A is less than or equal to the cardinality of B, meaning that there is an injective mapping between A and B, then since you know that A prime is equivalent to A, then there's a bijective mapping G from A to A prime and a bijective mapping H from B to B prime. So you can define a new injective mapping between A prime and B prime, such that you take A prime to A to B, and then B to B prime, giving you that this is an injective mapping at every step, so the composition will be injective. Namely, F prime is equal to H composed with F composed with G inverse. Therefore, since you have an injective mapping F prime, then the cardinality of A prime is less than or equal to the cardinality of B prime. As far as notation is concerned, you can also consider cardinality of B is greater than or equal to cardinality of A as an alternative way of writing this. And you write that cardinality of A is less than the cardinality of B, or the cardinality of B is greater than the cardinality of A, to indicate that there is an injective mapping, but there is not a bijective mapping, so the cardinalities are not equal. Since any finite set can be represented as a subset of n, but one that does not admit a bijective mapping to n, it follows that n is less than Aleph null for all n in the natural numbers. And for any infinite subset, E as a subset of the natural numbers, it is the case that the cardinality of E is equal to cardinality of n is equal to Aleph null, even if E is a proper subset of n. For instance, you can consider even numbers, and there is a natural bijection between the even numbers and the natural numbers. Therefore, they have the same cardinality, since cardinality being equal is defined up to there existing a bijection between the two sets. Indeed, each element of E is in particular a natural number n, so when these natural numbers are arranged in increasing order, n1, n2, n3, then you generate your bijective mapping F from E to n that associates to each ni in E the natural number I in n, and you have what you sought out to prove. If you read the footnotes, you can see that actually n is the smallest infinite set. It is somewhat counterintuitive that any infinite subset of n can have the same cardinality as n, or the same number of elements as n. Since if A is a subset of B, is a proper subset, and both A and B are finite, then it is the case that the cardinality of A is strictly less than the cardinality of B. But as we've seen, that is not necessarily the case for infinite sets. A further examination of inequalities among cardinalities of sets rests upon the next result, the Cantor-Bernstein theorem, which is evident for finite sets, but not obvious for infinite sets. Thank you. And get ready for next video where we will consider the Cantor-Bernstein theorem in its entirety. Have a good day.